Hello again and welcome to another session with the Cyber Professor. Today we will be talking about the evolution of memory management systems as part of our review of the operating systems course. First, to the learning objectives. We will be learning about paging, the meaning of paging and what page memory allocation system is. Number two, we will be learning about the demand page memory allocation system. As our third objective, we will understand the concept of segmentation and talk about the segmented memory allocation system. And finally, we will be talking about the segmented demand page memory allocation system. As part of our review of the operating systems course, we divided the course into different sections. We already covered number 1, Introduction to Operating Systems. Then we moved to processor management, number 2 in our course map. And now we are in the final session of number 3, memory management. As a summary view, what are we talking about again? In our last video, we talked about the early memory management schemes, and those were the following 4 schemes. Number 1, the single user contiguous. Number 2, the fixed partitions. Number 3, dynamic partitions. And finally, we talked about relocatable dynamic partitions. The characteristics that we talked about these early management schemes are as follows. The entire program needs to be loaded into memory. It has to be stored contiguously. And it needs to remain in memory until the entire job is completed, bringing the following challenges. With the early memory allocation methods, we require the entire program in contiguous locations in main memory. And that brings fragmentation, which occurs, and it requires frequent compaction. For that, and to solve these issues, we bring into the equation the alternative memory allocation systems, which are the subject of this video. The first one is the page memory allocation system. The second one is the demand page memory allocation system. Then we will move to segmented memory allocation system, and we will conclude with the review of the segmented demand page memory allocation system. Before we get into the important definitions, we need to understand how processes and jobs are handled by the computer system at a very, very high level. We need to understand that the programs are typically stored on disk, which is the permanent storage component of your computer system. From there, the operating system is responsible for loading the programs into main memory. Finally, the CPU executes the instructions loaded into memory in the previous step. So now, let's get into the important definitions. First, we define page as a fixed-sized section of a user's job or program that corresponds in size to the page frames in physical memory. Next, we define page frames as equal-sized sections or chunks located in physical memory. Next, we talk about segment as a portion of memory, physical memory that is, assigned to a logical grouping of code in a job or process. Next, we define physical address as the real address in physical memory or RAM. We move to virtual address and define that as the logical address relative to the start of a process address space. And finally, we define virtual memory as a technique that allows programs to be executed even though they are not stored entirely in physical memory. Here we have a depiction, a graphical depiction of your physical memory, this rectangle here. We see that the physical memory is being allocated to 3 different components or programs. The first one being the operating system, the second one being job X, and the third one being job Y. The first component that is taking your memory space in your RAM is the operating system. And as you can see from the numbers on the right, it is taking from memory address, physical address 0 to physical address 200. Job X, on the other hand, depicted in blue, is taking the physical address space from 200 to 800. And finally, job Y, which is depicted in orange, is taking the physical space in memory from 800 to 1200. On the other hand, on the left, we have the depiction of the virtual address in virtual space. And we can see that for job X, which is depicted in blue, the starting virtual address is 0, even though the physical address is 200. The ending virtual address for job X is 600, while the actual physical address is 800. The 600 is the difference between 800 and 200, which is the size of job X. The same applies for job Y. The beginning or starting virtual address for job Y is again number 0, and the ending virtual address is 400. The 400 comes from the difference between 1200 and 800, which is the size for job Y. That is the difference between the physical address and virtual address, explained with a high-level diagram of our physical memory. Now we move to the first memory allocation system we will review today, and that is the paged memory allocation. But before we do that, we need to bring into the equation a couple of components. The first one is the disk storage, which resides on your computer system. The sections of a disk are called disk sector, and the disk sector is depicted here in the dark gray. The next component we need to define is physical memory, which is depicted on the right. And the physical memory is subdivided into page frames, which are the small equal size rectangles that you see depicted here in light blue. The role of the operating system memory manager is critical in ensuring the appropriate allocation of memory to a program, because it first has to identify the number of pages that are part of a given program. And they are depicted here on the right or in the middle as Microsoft Excel being the example job or program that we will use for our review, which is divided in 3 equal size pages, named page 1, page 2, and page 3. Second, the operating system needs to identify the same number of available or empty page frames in main memory for all pages to be loaded, so Microsoft Excel can be loaded into physical memory. So the operating system in this example has identified page frame 1, page frame 2, and page frame 3 depicted in blue as available space in physical memory that can be taken by Microsoft Excel, and the 3 subcomponents of Microsoft Excel being depicted here as page 1, page 2, and page 3. Finally, the operating system is responsible to manage pages in memory. By that, we mean moving, removing, and reallocating pages in memory. Please note, there is no need for contiguous memory space in physical memory. Here we have a depiction of 4 different programs that are part of a computer system: Windows operating system, Microsoft Excel, WebEx, and Microsoft Word. In the eyes of Microsoft Excel, the program is taking the entire memory space available in the computer system. Each of these 4 jobs believes it has full control of the entire memory. The operating system allows for each of these programs to behave this way. A program's view of memory is called logical memory. Now comes a different component. In this case, physical memory, the actual RAM that resides on your computer. As you can see from this depiction, Microsoft Excel is divided into 3 different pages. These pages reside in the view of memory that Microsoft Excel has of our computer system. And that view is the logical memory view that we have depicted here in the middle. In this view, 3 contiguous spaces are taken by Microsoft Excel and nothing else. Only Microsoft Excel resides in memory, in the eyes of Microsoft Excel. However, these pages have been allocated to physical memory in the form of page frame allocations, as depicted here on the right. Page frame A1, page frame A2, and page frame A3, depicted in green. A single job may occupy multiple page frames, which are not necessarily contiguous in physical memory, as you can see from the diagram on the right. In order to keep track of the allocation of physical memory space and the relationship with logical memory, the operating system must maintain a table that maps logical locations with physical locations, as depicted in this page map table here in the middle. Here we have a view of 4 different programs. They are logical views individual to each program. In this case, we are depicting the logical view, the logical memory of Microsoft Excel, and the Windows operating view of memory as depicted here, the logical memory of the Windows operating system program, and how the allocation in physical memory can take place, and it can change. It can use contiguous space, or it can use space that is not contiguous in physical memory, as depicted here in green for Microsoft Excel. Characteristics. There is significant overhead for this first memory allocation system that we have reviewed. The operating system must keep track of memory allocation, which means keeping track of the page frame in memory in which the page is located. The memory management module of the operating system fulfills this responsibility by using 3 different tables. Number 1, job table, which maps the job size and the page map table location. Number 2, page map table, which maps the page number with the page frame number. Number 3, memory map table, which maps the page frame and the corresponding state of each of the frame, either busy or free, to indicate if the memory has been allocated or not. This brings complexity to the equation. Second, we will review the demand page memory allocation system. The characteristics of the demand page memory allocation system include the fact that it is very similar to page memory allocation. However, pages are only loaded on demand, meaning they are only brought into memory when they are actually needed. That keeps only those parts of a processing memory that are actually being used. It removes the restriction of having the entire job in memory from beginning to end of the processing. And finally, it takes advantage of the fact that programs are written sequentially so that while one section or module is processed, other modules may be idle. In this example, we see Microsoft Word as the job that is about to be loaded into memory. The operating system, Memory Manager, identifies that only page 2 and page 3 are needed at a given point, while page 1 and page 4 are not needed. By following the rules of the demand page memory allocation system, the operating system loads only page 2 and page 3 into physical memory by loading them into the corresponding page frames that are depicted in red in physical memory. Demand page memory allocation system brings another table into the equation, and that is the page map table. This page map table increases by 3 more columns compared to the first memory allocation system that we reviewed, and those are depicted in yellow. The first new column indicates the status of the page and whether it is already in memory or not, and it is depicted in yellow with a yes or no for each of the page frames that are listed here. The second new column indicates whether the page has been modified or not, and it is depicted in yellow in our diagram. Finally, the third new column checks if the page has been referenced recently with a 1 or a 0. So how do we determine how to replace pages in our computer system? We do that by choosing from the following page replacement policies: first in, first out, least recently used, most recently used, and least frequently used. These are policies used to change pages based on specific algorithms. There is a significant cost of paging in your computer system. The operating system needs to be able to maintain a complex set of tables to keep track of memory allocations. The translation look-aside buffer, or TLB, is typically required. TLB stores page numbers and the page frame association. Finally, translations between virtual and physical address increases the time latency. The third memory allocation system we will review is the segmented memory allocation. The characteristics include the fact that the process of dividing a job into variable size sections of a user's job that contains a logical grouping of code brings the concept of segments. Follows the concept of the user's view of a program and divides it into pieces that make logical sense, like, for example, global variables, stack, heap, rather than a byte sense, which is used by the paging memory allocation system. So here, we divide a job into segments because we want to create different chunks within our job that make the most sense based on the way that the program or the job is behaving or is working. So that is why we come up with different sizes for those segments, different from the equal size units that are part of a paging memory allocation system. With paging, we must stick with equal size units of the job or the memory space, depending whether or not we are talking about the page or the page frame. With segments, we can divide our jobs, as the one depicted here in the middle, being the WebEx program, into different size units. In this memory allocation system, we call them segments. So that is why you have the WebEx program or job divided into 3 different size segments that are called segment 1, segment 2, and segment 3. And as far as the memory space that is allocated to these segments, you see them depicted here in physical memory on the right. So what is swapping? Swapping is the rollout of a process to disk, releasing all the space in physical memory that it holds. So when the process becomes active again, the operating system must reload the job from disk into physical memory. If swapping is part of the system, compaction is easy to add, meaning when swapping is taking place, that is when compaction can take place. That is the right moment for compaction to take place. So in the diagram that follows, we can see the different allocation of physical memory to 4 different programs: Game, Microsoft Excel, WebEx, and Microsoft Excel depicted again here. So we see that they are occupying space in physical memory. However, if physical memory becomes scarce at some point in time and there isn't enough space for a new program to be allocated in physical memory, some of the idle processes that reside in physical memory, in this example being the red section of the game that is depicted here on the bottom of physical memory, can be moved to the permanent storage, which is the hard drive on your computer system, in the form of a swap file allocation. So you see this red portion of physical memory being vacated and moved to the hard drive on your computer system. The reason why you're doing that is to free up space on physical memory so another program that is waiting to be allocated in physical memory can take the place of the game allocation that is here in red and can utilize some of the physical memory that has been freed up by the movement of the game processes or jobs into hard drive or the swap file on the hard drive. So in this case, we see that the segments are swapped between disk and main memory as needed, meaning back and forth. Large segments may not be allowed into memory very often. So if you moved a segment into the hard drive and then you try to bring it back to physical memory, but if it happens to be that your physical memory is almost full, you will not be able to move that large segment back into physical memory right on time for the processing of the CPU. So that's one of the challenges that you will be facing when you are utilizing the swap files. Each segment is atomic. Either the whole segment is in RAM or none of the segment is in RAM. This is important to know in the segmented memory allocation system. Segmentation can result in fragmentation. And fragmentation takes place when jobs are deallocated from memory, meaning they were fully executed. So for example, in this blue section, the WebEx program, when it is fully executed, this space will become available. But then the following job that comes into play wants to utilize only a portion of this blue space, and then it creates mini empty portions between the green and the red, and that is creating fragmentation in your physical memory. So what is page displacement? In a page or segmented memory allocation environment, the difference between a page's relative address and the actual machine language address or physical address is called page displacement. It is also called offset, and this is an important concept that you need to understand for our review. Next, what is cache memory? A small, fast memory used to hold selected data and to provide fast access. This is the traditional view of an old computer system. You have the hard drive that stores the programs that reside in your computer system. Some of the processes and the jobs are loaded into memory, and then the CPU is responsible for executing those instructions from memory. This is a very slow view of a computer operation in the traditional way. Modern computer systems utilize cache, which brings another layer between the physical memory and your CPU. In this case, the hard drive stores the programs. Some of the processes and jobs are loaded into memory, physical memory that is, and the most used sub-processes or jobs reside in cache, so they are readily available to the CPU for faster processing. This is the view of a modern computer system. Finally, we will quickly talk about the fourth memory allocation system, and that is the segmented demand page memory allocation. The question is it possible to get the best of paging and the best of segmentation for a more robust option? And the answer is yes. We can maximize segmentation's ease of sharing and paging's efficient use of memory into a new approach, and that is the segmented demand page memory allocation system. The characteristics are as follows. It is a combination of the segmented memory allocation and the demand paging memory allocation. It offers the logical benefits of segmentation as well as the physical benefits of paging. The same logic and virtually the same algorithms are applied. It does not keep each segment as a single contiguous unit, but subdivides it into pages of equal size that are smaller than most segments and are more easily manipulated than whole segments. Many of the problems of segmentation, by that I mean compaction and external fragmentation, are solved because the pages are of a fixed length. And that concludes our review of the alternative memory management systems that were the subject of our discussion today. And with this, we conclude the memory management section of our course map that we were supposed to complete before we moved into the next section. Until next time, thank you very much.